All right, so for tutorial today, I think there are two things I would like to do. So number one, I would like to definitely finish off about how you can do rotations after deletion. I think that it's still case number 4 of the BST deletion we have to review quickly. I'll do example and overview the steps so you can also study for that. And then we'll talk about what kind of steps you should really take to really restore the balance for BST, by doing some tri-node restructuring step, basically either one single rotation or multiple rotations. We'll see how the time goes. So this part here, I'd like to do in the second part. But for the first part, I want to do a little bit of Eclipse programming. Not really to develop something from scratch, but I do have some exercise which I already designed over there. I'll show you where to find it. But I think that you guys should really take about a week, or maybe just a few days over the weekend. So we'll go over the solution next Friday when we come back. It's really good for you to struggle a little bit with that exercise. It's not difficult, but at least you get some simple version to see how you can implement tree rotations. And then for your assignment number 1, which is going to be released during the reading week, I'll make it a little bit more complicated for you to try it out. So that'll be a good setup. Okay. So let me show you how you can find out the tutorial materials, okay, just in case you haven't found it. The tutorial videos will always be on the lecture side, not the e-class, okay, always. Maybe for your assignments and also assignment instruction and solution, I'll put it on the e-class. But for tutorial, always on the lecture side, okay. So if you go under here, so it will be under tutorials right here, right? Week number 4. So should be 26. Okay, not 16. Okay, I'll fix that. Okay, so we're doing self-balancing binary search tree. So the first document here is the instruction, okay, right here. So there are basically 2 things we want to do this week. So this section number 1 is something that I just mentioned. We're going to do some deletion and also to see how we can do restore the balance. We'll do some example on the paper, okay? But I'll start with section 2 just to let you know what you should do. So we're going to see how you can download the starter. And also, you have to look at some classes for Java. So the BST node class that we presented in the lecture time, I extended that a little bit by just a few lines. I want to show it to you just to make sure you feel comfortable. It's actually very basic Java you learn from maybe from 2030, right? It's not difficult, but I'll point out to you so you can be aware. And also, I'll go over with you very quickly about several test cases that currently do not really pass at all. So maybe you can take maybe up to the week, maybe before next Friday, you can try to see if you can solve the problem by yourself. Of course, you're welcome to reach out to my office hour. Maybe in the coming week, I can also help you with that. You can think about it as like a very mini assignment for you to try. No submission required, but you definitely want to try. Could be covered in the test. So there are 2 things. One is just about in-order traversal, easy. And the second one is about how you can do the right rotation. So I would say this might be the simplest one. You can actually try it out first. And then I will make it slightly more complicated, adding more context, maybe in your actual assignment. But give it a try here. It may not be as trivial as you might think the rotation should be done, okay? There will be some edge cases you have to handle, which the JUnit test cases should be able to help you capture them, okay? So these are the 2 tasks that we want to complete today, especially for maybe section 1. I'll try to at least go over the principle with you and then at least do 1 or 2 examples. Let's say hopefully at least 1. If time permits, we can do both. If not, then we can maybe assign to you. You can do it, and then I'll give you a solution. Okay, so that'll be the plan. All right, so let's now, if you haven't, you can click on the Java icon here, right? You can click on that. That's going to be the starter projects, okay? Okay, you can download it maybe to your desktop, wherever. Okay, it's on my download folder. So, and then later, this is notes template, which I'm going to go over today. Okay, so these are the clean pages you can actually download and take your notes, right? Just like the lecture notes, really. And then I'll put a recording later today, and also the annotated notes. Okay. So let's now just switch to Eclipse very quickly, right? So I wouldn't do any programming today per se, but I just want to point out to you the things you're going to complete in the coming few days, right? All right, so again, how do you import? So let me just show you one more time. So File, Import. Under General, you click on Existing Projects into Workspace. So this will be something similar to what you have to do in the upcoming 2 midterm tests in the programming component. So next. And then, of course, you're going to say select archive file, and you're going to browse to wherever you actually store the starter project. For me, it will be, for example, let's say the downloads folder, right? Just click on that, and you should be able to import. For me, I already imported it, so I don't need to. Okay, I'll just cancel for my case. Okay, so that'll be week number 4, September 26th. And then if you click on the source folder, so there are 2 things over here, right? So we got the model package. It does have something here, okay? It's something called BST utilities, right? If you double click on that, what you will see is 2 methods unimplemented. So I also put down some library class you can consider using it, especially array list. So when you do the in-order traversal, you may have to use an array list rather than just primitive array. Just make it a little bit easier, okay? So that'll be the first one about in-order traversal. Also, the in-order traversal is also being used in the JUnit test cases. You definitely want to get this one right. I will just explain to you about the in-order traversal we are doing just for this task. It's slightly different from the standard one, but that's okay. I'll explain clearly to you what we're expecting to see. And then we also got another one, which is called a right rotate. Okay, so this one here is not. It's very isolated right rotation. We're just saying that I'll give you 3 nodes, A, B, and C, do the rotation, and that's it. Okay? You don't really have to check anything about the balance, or maybe check to see maybe after the rotation if the tree actually was established to be balanced. You don't have to. Okay? We don't really do that complicated stuff just yet. So for this exercise here, just to see how you can use the references assignments in Java like OOP to really do the rotation. That's all I want you to try. And there is some link over here. You can actually go over basically the relevant slides. Okay, you can also go to the link and take a look. All right, so these are the 2 tasks you can try implementing. Hopefully, it wouldn't take you more than 1 hour, really. You know, maybe 20 minutes, 30 minutes. Okay. Okay, so that will be this one here. And then I want to start with talking about the BST node. Okay, right here. So in the BST node class, pretty much the same as what we said in the lecture. Okay. I slightly extended 2 methods there. One is the set left. The other one is the set right. Okay? So the lecture version is still valid, but the lecture version only say, I want to say this.left equals left, the parameter. But I say another one over here to also set the parents symmetrically. Okay? That's something I want to show to you. So this one here is also very important to update both the child and also parent references at the same time. Okay? I want to show you very quickly. Okay. So just for this one here, I'll get to the deletion maybe in the second part. Okay, let's get the first just the programming part. So just about construction. So when you, I'll just explain to you just about some very, very simple usages of the set left and set right. So we talk about the BST node class right here. Okay, so that's the class we are talking about right here. Okay, and then we talk about the set left and also set right. Okay, I'm just going to trace the code very quickly with you just to see how it works. However, this simple example here is definitely, well, it's very simple. Just building like 3 nodes, including 2 external nodes. But what you should really do is this. Take a look at this tree, which is I took simply from our slides. You can see for this particular tree over here, we got 2 kinds of nodes. We got internal nodes like these, and also we got external nodes like these. How do you build a tree like this, right? So you can take a look at one of the test methods. Okay, let me just go there to show you where to find it. And then I'll talk about a simple example, so that will definitely help you understand. So go to the testbst.java is a JUnit test class. And then you can go to, there is a helper method right here. Okay, the helper method here is called construct example tree. Okay, so this is the example tree we are using for this particular tutorial. That's the one. And that construction over there, you can see how we create the new node objects and also how we actually set the left, set the right, etc. to really build a tree. Very straightforward, right? So if I kind of give you a tree similar to that, maybe slightly less complicated, maybe during the test, can you build something like this, right? With the left and right set up properly. Okay. Okay, let's now take a look at some very simple case. Okay. So let's say this, just a few lines of code right here, all right? So we talk about how to create individual nodes. So let's say for this one here, we got N44 right here, okay? So N44 is pointing to a BST node. And we have quite a bit of attributes right here, okay? Let me just review what we said earlier in the class. We got parents, and also we got left child and right child. Okay, so one is the left child, and the other one is the right child. And also we got the key and the value. Okay, also we got the key, and also we got the value. Okay, so let me just copy this because every object will look the same, every node. Let me just copy that. All right, so N44 is going to be 44 here, and also that's a value. Okay, so I'm going to put 44 and also the data. In the beginning, everything will just be null. In the beginning. Okay, very straightforward. Okay, and then we're just going to create two external nodes. We got one here, and also we got one here. Okay, I'm just going to create these two. Okay, one here. But that one ought to be purple. Okay, I just change the color of that. Okay, this is one, and I got another one here. Okay. Okay. There we go. Okay, so and then we got EXT external nodes number 1, and also we got external node number 2 right here. Okay, we got 2 of them. And also in the beginning, in the external node, it doesn't store anything useful just yet, right? So everything will be null or default value. So here we just got null over here. And the key value, we're assuming that is simply just minus one, just integer. So for example, it could be just -1 for invalid. Okay, value here will just be some objects, but also null. Okay, null, 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 null. Okay, now let's go over the set left and set right. Okay, but maybe let me just do a set left. It'll be very obvious to you about how to trace a set right. Okay, very similar. So let's say I'm calling this method here, right here. Okay, set left. And then N44 is the context objects, right? So when I call this one here, every occurrence of this is going to be N44, including this right here, N44. All right? And of course, this one here is calling set parents. So I don't really have set parents over here, but you can kind of imagine how the set parent is going to work. Simply set a parent reference to that particular node. Okay, so that detail is omitted. And then we got right here the arguments, external node 1. So here will be external nodes 1. And here will be external nodes 1. And then, of course, this one will be also external nodes 1, right? So it's really about this particular one, just in case you're not comfortable passing this in the Java, right? You should be, you know, it's something you did in 2030, but maybe just forgot about how to do such things. So it's good to review. So now how do we execute this? This one here, we say N44 dot left child is external node 1, which is right here. All right, that's what we do. So this line here, okay, let me just say this line here is actually going to say, rather than pointing to here, rather than storing null, is actually going to point to wherever external node is pointing to. Symmetrically, it's also going to set external nodes 1, parents to be N44, right? So that's symmetric link. So that means symmetrically, we're going to say external node 1, parents, rather than null, is going to point to N44 right here. So we got a bidirectional link, okay, right there. Okay. So one thing that's very important, well, actually this method here will save us lots of trouble. So whenever you want to do rotation by setting the left and right or parents, well, you don't really have to explicitly set a parents unless you really have to. But normally when you say the set left and set right, it's going to update the parents at the same time, right away. Right? So this can be one version of the method you can try. All right, so for the set right, I'll let you trace it, right? That should be just the same. I don't need to waste your time. Okay. Any question about this? Simple stuff, right? But I just want to mention. Okay, and then about in-order traversal. Okay, I want to mention something quickly here. So this is something you will have to implement, very easy to be done, especially recursively. So in order traversal is going to return an array list. So this is the method we are calling in order traversal. Okay, and then it's going to take some BST node. You can think about this one here is a starting root, the root of some subtree. This is starting point. So in this case, we say we want to start from here. So this will be N44. The convention is I put part of the name in the node by its key value. Okay, so we're going to start from here. And then the in-order traversal is going to be very similar to what we are used to, except that we want to include in the list also the external node references. So this is just for us to really also make sure we have done the tree rotations properly. Okay, so the way I named the external node is like this. So this one here is called external node 1. And this one here is 2. Okay, and this one 3. And this one 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14, 15, 16, and 17. So we got 17 external nodes, okay? And also 16 internal nodes. So we got 33 nodes in total in the in-order list, all right? So that's what you will see. So you gotta make sure you kind of modify the conditional, maybe in the standard in-order traversal to make sure this can work, okay? So for example, you will start with the very first one should be external node number 1, right here, followed by 8, followed by external node number 2, and then followed by 17, etc. All right, that's a whole list. So this is just one test case to really show to you, but you can feel free to write additional one if you want to. So that's your first task to implement. Okay, should be straightforward. Of course, if you want to try, you can try pre-order and post-order as well, right? That's also something you learn from 2101. Yeah. Any questions about what you should do for this one here? This one, I would imagine if you still remember the principle, maybe take you a few minutes to get it done. You just got to make sure you actually include all the external nodes at the bottom here as well, the leaf nodes. Okay? The next one, about rotation. Okay? So that one there, you will see that in the starter projects there, also in test BST, right, over here. So I got 3 test cases for you at the moment, okay? So I got test BST right rotation 1, and also 2, and also 3 over here, all right? So I'll maybe show you maybe 2 of them, just to show you conceptually what is something you have to pay attention to. And also notice one thing here. I put here the expected in order traversal after the rotation is done. Okay, so that's something I'll mention as well. But notice that I put T1, T2, and also T3. And also I put C, B, and A, right? The reason I put this, I'll show you a reference, okay? If you go to the actual code, right here, right? So the hints, if you simply copy this link, right? Let me just show you that link. So this will give you the hints about how things are supposed to be done, right here. Right, so if you follow the link, it's going to show you this page here. Remember we went over this in the class, right? To say if you actually already got A, B, and C, they all slant to the left. In this case, you want to promote the middle node B up to be the root. So you're doing a single right rotation, right? So you can see this is before the rotation, and this is after the rotation, right? That's the single rotation we're doing for this exercise here, just a simple one. And later on, we can maybe extend that to be the left-right or right-left, or maybe do multiple rotations, right? That's something we'll do later. But just get this simple one done. So that would be your more like a conceptual guidance about how things should be done. And given this abstract diagram here, how are you supposed to identify T1, T2, T3, T4, first of all? And also, once you know about T1, T2, T3, T4, and also A, B, and C, how can you kind of restructure them by setting left, right, parents, etc. Right? So that'll be your task. Okay, so let's now take a look at something here. Okay, for example, how do you read a test case? So you can see here we're calling the method right here, right rotate. You can see first of all, we call this helper method construct an example tree. So we do have a tree that looks like this. Okay. And the right rotate will give you 1, 2, and 3. So we assume the following. So we basically got A, and also B, and also C. Okay, so for this particular test case, so this is A, this is B, and this is C. Okay? After the right rotation, right, you can just conceptually after this, after the right rotation, the new root is which node? What will be the key for the new root? 17, yeah, okay. If you haven't done this before, if you're not exactly sure, you may want to review the stuff, right? Now would be the best time. Since we're doing some rotation here, they all slant to the left. So we should really rotate B to the right by 1 level. So B will become the root, all right? So it's going to become something like this. So it's going to be B, and then C, and then A. So B here will be the new root. Okay, so this exercise is very valuable. It somehow put what you learned in theory in the class on paper into Eclipse. You really got to make sure you know how to make it work. New root. So that is why when we do the in-order traversal here, for us to get an entire tree, we have to start from N17. You can think about the N17 here is really the B. All right? So this is the new root, not the old root. If you only start from like an N44, it's not going to give you the whole tree anymore because after rotation, it's not the root of the whole tree. All right? So that's why. However, if you start from here, the in-order traversal order will be just the same as with before the rotation. If you compare this order over here, right? This is the in-order traversal exercise. This one here before the rotation, also after the rotation, the sequence for doing in-order traversal will just be the same, identical. It's just the structure of the tree that's being changed. That's another thing you want to also notice. All right? Expected order here is actually identical. Identical to the in-order traversal sequence before the rotation. Okay, that's one test case. Okay, so here A, B, and C, where A happen to be the root of the tree. I'll give you another test case, right? Let's say test case number 2. We're still calling the right rotate. Let's say right here. Right here. All right. So this time we still got past the A, B, and C. So here we got, let's say, A here, B here, and also C here. Okay. So we got A, B, and C. So A is 32, and B is 28, and C is 21. So now I can tell you that the tricky thing, well, not really tricky, but you just gotta see exactly how to handle that programmatically, and you definitely know how to do it. The difference is when you do the rotation, right? You gotta make sure this particular subtree is gonna change its structure. And the new root for this particular subtree is going to be 28. And somehow 28 should be connected as the right child of 17. The right child of 17 used to be 32, but not anymore after the rotation. All right? Diagrammatically, it makes sense. How do you make sure it's going to be done in general in Java? Right? So that's something I want you to think about as well. You might need some if conditional, somehow to handle this. It's not difficult, right? You got all the getter and setter from the BST node. I got everything ready, okay, available to you. So after this one here, because we're only restructuring this particular subtree by doing the rotation on B, so 44 remains to be the root, right? So it's still the same root. So that's why the starting point for in-order traversal is still the same, all right? You can say the following. The rotation does not modify, does not alter the root of the entire tree. All right, and there's another test case which I didn't include over here, but it's similar. If you look at the test case number 3, it's very similar to test case number 2. I just gave you another part of the tree. So I will show you here. So if you go back to the test case, the rotation test case number 3 over here, right? So this case, we are still starting from N44, the absolute root of the tree. That means we are still just doing some local rotation as part of the subtree, right? So take a look at this one as well. Okay, well, I think that these 3 test cases should be able to guide you about how to implement the rotate for right rotation. Okay. And then I'll give you something a little bit more sophisticated, maybe in the actual assignment. So at least for this one here, can prepare you well for the actual assignment or even for the test, right? Hey, okay, any questions about the programming exercise here? We're good? Okay, so try them out, and then next Friday, we'll still be in person. I'll be here. And then I'm going to start by going over the solution with you. And then I can maybe suggest some additional exercises you can also try. Okay, so that'll be one part. I would suggest we do a little bit of paper exercise and before we take a short break. Okay, why don't we do something here? Okay, we still got maybe 10 minutes before halfway. So why don't we just do about 10 minutes? Okay. So let me go back to section 1, which is about the BST deletion procedure. Let me just finish that part, and then we take a short break. Okay. So in the lecture on Wednesday, so we spoke about case number 1, 2, and 3, so they are well understood. So I just want to talk about case number 4. Okay. Somehow case number 4 will involve invoking also case number 2 and 3 as helper methods somehow. All right. And in your coming assignments, which I'm going to release at some point, maybe around the reading week, I'm also going to let you implement the insertion and deletion for BST. I think it's also worth doing. Okay? It's something that we didn't really have time to really do in 2101, but I think in 3101, it's also a nice way to implement algorithms like this. There will be some implementation details you have to think through as well. Okay? That's something we'll let you try. It's kind of fun exercise, actually. Okay, for case number 4. Okay. So we say that the P here is really something that's returned by the binary search, okay? And the P that's returned, somehow they got both children being internal, okay? In that case, we just cannot just remove P, in which case both children are gonna become, they call orphan subtrees, right? We cannot do that, okay? So both are internal. So we're gonna see an example, okay? So both are internal. So the idea is like this. Okay, let me draw something here right away. So let's say, for example, let's say the one we are trying to delete is R. So case number 4. Okay, I'll draw something just to sketch the idea. And this is actually something we also went through when we reviewed the BST. Okay, so let's say the R. Okay, let's say right here. So for example, let's say this is the node to delete. For example, and that one there has 2 children, right? Both child nodes are internal. So I have one internal child over here. I got another internal child. And they might have arbitrary subtree underneath it. And now the question is, how do we somehow delete this guy here? Right? We want to delete this. Okay? So this is the P that we're talking about. All right? How do we delete it? Apparently, you cannot just get rid of it. That's not the way to go. Right? We're going to do some replacement. And to really see what kind of replacement we can do, you got to think about when we do in-order traversal, what comes before this node to be deleted? Well, what comes after? You can do either way. All right? So if you do in-order traversal, for example, right? Again, let's review. We have seen this diagram in the lecture, right? Just review that. Let's say N1, N2, N3, P, and then N4, N5, N6. And somehow the way I can label them can give you the order already, right? So if you do in-order traversal, you're going to go for the minimum, which is N1. And then at some point you will reach M2. And then you'll go to M3. N3 is going to be the largest key that is smaller than P. All right, and then you go for P, and then go for N4. Okay, let me just write it down, and then I'll talk about it. So just go up here, right? When we talk about in order traversal, we got N1, followed by N2, and at some point N3. And then we got P, and then we got N4, and then we got N5, and then we got N6. That will be the sequence, okay? So the step is going to be something like this. Of course, you can read the textual description as well. I'll just show it to you, okay? We're going to see two different cases, but they follow the same principle. The idea is we want to remove this guy here, but we cannot just remove it directly. What we do is we can do replacement. Either you can try to say, I want to replace the value over here and put it over here. Step number one. You basically replace P by N3. I'm not removing anything just yet, right? And temporarily, you have N3 followed by N3, but that's okay. And then N3 over here has the special feature. N3 over here, for example, is the rightmost node in the left subtree of P, right? According to the geography, right? It's the rightmost node. If it's the rightmost node, there are only two cases, okay? N3 over here, only two cases. N3 over here, only two cases. Case number one. N3 may have just two external nodes. Or case number two, it may be that N3 has one internal and one external. So these are the only two possibilities. Okay? And one question which is on the slides. Is it possible, okay, so here's a question. Is it possible that we have N3 over here, and then somehow we got another internal nodes, and etc.? Is it possible? How come? That's a very critical question, but I'm glad that's the right answer.
It would not be the rightmost node.
That's exactly right. All right? So it's very important. So this is something I want to point out, guys. So the reason that we got two sub-cases for case number 4, it says that either N3 over here has two external nodes right here, or has only one external node. You might be wondering, is it possible it has no external nodes? It's not possible, because if this is internal, then N3 wouldn't be the rightmost as we illustrated here. It's kind of contradictory. Right? It's a point you want to make sure you're convinced. All right, good. All right, so that's about the sketch. So what we do is, after we have done the replacement, we are now going to remove N3. So N3 here can either be removed in this case, or it can remove in this case. Okay, this case over here is really the case number 2 that we spoke about earlier. Okay, and this over here is really the case number 3 that we spoke about earlier. That's why I said it's more like a calling. The delete method is a helper method. That's something you will try when you do the assignment later. Okay. All right. So step number 1 would be to replace, and step number 2 is to just remove N3. So we only remove this guy here. We don't really remove this one here. That one there, we just replace it, but it'd be as if we removed the key already. All right? That's really case number 4, right? We got 4.1, 4.2. Why don't we do that very quickly, and then we'll take a short break. Okay? Yeah, really take a look at this slide here. It really summarizes all the 4 cases you got to handle for deletion. But let's now do exercise here. Okay? So let me just identify which node we're going to remove in. Oh, question. Go ahead, please.
So in the case where N3 has one internal, one external,
Yeah.
if we replace P with N3, what happens to P's internal child?
So here, okay, sure. So we're basically talking about this case over here, right? Okay, so good question. So let's say we are running into this case, but we're going to see that anyway, but I'll mention that conceptually. So let's say we are in this case, and where N3 actually got, let's say, some internal, and also, okay, sorry, let me draw it again. It got some internal, and also it got some external. What we can do is we can simply replace this value, let's say this is x, put x over here, and then remove it. That's what we can do. That's exactly what case number 3 would do, which you can review. But I'll do that again here. Okay? Good. All right, let's now talk about these two cases. So we want to remove 17, right? So let me ignore the binary search process because you know how to do it. Question?
Can you replace P by N4?
Yes, you can. Okay, that's good. It's actually one of the also exercises I put there. Okay, I'll put it here for you. Can R contain the smallest key such that it's larger than, right? That's exactly the question here. So guys, another point for you. Here we are saying we replace the P by N3. Can we replace P by N4 and then delete N4 instead? The answer is yes, you can. Because in terms of in-order traversal, N3 goes before P and N4 goes after P. So if you want to do the replacement, as long as it's go right before, right after, you'll be okay. But don't do both. Okay? So either you simply replace P by N3 and then delete N3. Solution number 1. Solution number 2, you can replace the P by N4 and then delete the N4. It's also going to be guaranteed the way M4 is going to look like. But of course, you're going to define the solution accordingly about which case you want to involve. Right? Good question. All right, let's now do these two examples, and then we'll take a short break. Okay. So let's say 17 that we want to delete, right? 17 is right here. And the path we're going to follow will be, so from here and then all the way to 17, right? So we want to delete this guy here. So this is P. And let's say we want to delete N3 right here, right? It's going to be the rightmost node in the left subtree. This is the left subtree of P. And the 8 here happen to be the rightmost node, right? It's actually a very simple tree, but that one is just the rightmost node, okay? Rightmost internal node. This is the rightmost internal node. Okay, let me just pause over here, and then let's see another case, okay? How about we want to remove 88? So we're going to say 44, and then go to 88, right? So let's say that's the one we want to remove. So this one here, we got 88. So this is the P, all right? And then we want to find out in the left subtree. Okay, let's identify the left subtree right here. This is the left subtree of P. And then we know that this 82 is the one we want to replace. So 82 over here, right, is the rightmost internal node. So this one here is the rightmost internal node. All right? And we're going to perform the two steps the same way in these two cases, right? Number 1, we're going to replace this node here, replace its value for this. Also replace its value for that. That one is going to preserve the in-order traversal because they are the predecessor of the 88, right? The in-order traversal. So step number 1. So step number 1, we're going to replace 17 by 8. Temporarily, we got duplicate, but that's okay. Temporarily. And then also step number 1 here, you're going to replace 88 by 82. Okay? And step number 2, we're going to delete the duplicates. Also delete the duplicates, right? This case, easy, because the node we want to delete already only got 2 external child. You can just delete it. This is case number 2. Okay. So delete this one here. Delete 8. And this is case number 2 in our algorithm, right? Exactly case number 2 when both child nodes are external. Case number 3 is one of them is internal. Okay. So now this one here, we want to delete the 82. And that one there has just one internal child, in which case you can simply, again, you can replace 82 by 76 and then delete 76. Well, that's what you can do, right? Okay, I'll let you do that one. Okay. So this one here is number 2, delete 82. 82. Okay, I'll try to write better. 82, and that is case number 3. Okay. So just remember, for case number 4, you will have to somehow also call either case 2 or case 3 to terminate that particular case. Okay, just remember. Okay, so I would say before the assignment is released, at least get yourself very convinced and understood about the principle over here, about the 4 cases. So when I release the assignment and let you program the insertion deletion, you just gotta have this page ready and have the example understood and then program it accordingly. There might just be some very minor implementation detail you have to watch out for, but it's gonna be very valuable exercise to do. Okay. If no question, why don't we take a short break, 3 minutes. All right, so we have already covered, review the principle or algorithm about deleting a node from the binary search tree. There's 4 cases, and for case number 4, you got 2 sub-cases, which can boil down into case 2 or case 3, right? So that's the high-level review you want to do. All right, just do the exercises, so that later on when I assign the programming assignments to you, you will know how to proceed at least, right? It will be some good struggle to really learn about the material. So let's now talk about how we can restore the balance after deletion, okay? So let me show you the slide number, okay? So give me one moment, I'll show it to you right here. Oh, sorry. Let me do it again. Okay, so insertion is already covered in the lecture. So what we want to do is now deletion, okay? So I think, after insertion, there we go. Okay, this one here. So slide number 32 is the algorithm I'm gonna go over. It's not that challenging, it's just slight extra care we have to, okay, to really see how we can do deletion. I'm gonna do some example together with you, like how we did in the lecture, just one. And then there will be another one, which I can leave as an exercise, you can try it out together with the Java exercise. And then I believe I have a video solution to that complicated exercise. I can release that, you can also go over. Or at least I can give you the paper solution, you can also give it a try. Similar principle, okay? Okay, let's now take a look. That algorithm, okay? All right, to start with, this insight is actually very important. Okay, I'll highlight it. Deletion from BST. Okay, this is something we just went over. Okay, about the 4 cases. Let's look at this claim here. It's saying that whenever you want to do a deletion from a binary search tree, it's going to result in removing a single node, sure, but that node there has 0 or 1 internal child node. It might sound a little bit weird, or you're not exactly sure about this claim, right? Okay, let me just tell you how you can really go back to the deletion algorithm and double check this claim, right? But you gotta think more about why this claim is true, okay? Basically, there are 4 cases. Let's now review back to case number 1, 2, 3, 4 and see if there's ever a node that's to be deleted, not to be replaced, but to be deleted. The node that we're going to delete is always a node that has either no internal node or has only 1 internal child node. Okay, let's see if that's the case. All right, case number 1, nothing to remove. So we don't need to worry about this case. The claim is true for case 1. Okay, and for case number 2, we are basically removing a node has 2 external node. That means no internal node. So the claim is true. Right? 0 or 1 internal node. So case 2 is fine. And for case number 3 over here, we actually got P here, we want to remove R eventually, right? And R, we want to remove the P eventually. And P is indeed a node that actually has only one internal child. So that's also true, the claim, right? So for case 2 and 3, So for case 2 and 3, that claim is true. What about case number 4? It's also true automatically. Because remember, the way we understand about case number 4 is, we first of all do some replacement. We don't really delete this node exactly. We try to do some replacement, and then we delete either N3 or N4, either way. And for N3 or N4, you will just boil down into either case number 2 or case number 3. So the claim still holds. All right? So when you actually review just this part over here, think about the different cases, especially for case number 4, you just boil down into case 2 and 3. So the claim is always true. Okay? Okay, so that's important. Okay. All right. The algorithm simply say after you delete an existing node, and the node has a child, n, internal child. There's only either 0 or 1. Okay, internal child. Okay, the child. The internal child. Which we'll see in the example. All right. So we got basically 2 cases, 1 and 2. Okay. Case number 1, if you somehow, this one here will be very similar to insertion. You go from n and then go all the way up to its ancestor path. Think about this as n over here. You actually go all the way to the root, the ancestor path. Okay. So this part over here is the ancestor path. Ancestor path of n, all the way up to the root. And then you're just going to find out the very first or the lowest node that's actually unbalanced, which is similar to insertion, and then do some rotation there. All right? And notice one thing right away, the way we phrase about deletion, right here. As unbalanced ancestors are found, you gotta keep applying case number 2 until case number 1 is satisfied. What does that mean? That means in the case of deletion, there's no guarantee the balance can be restored by a single or double rotations. You may have to do multiple trinode restructuring steps. That's the complication for deletion. Right? This one tells you there might be multiple trinode restructuring steps to perform. Multiple. Right? That's very important, right? The exercise I'll let you guys try is going to involve, for example, 2, all the way until the root, 2, rather than just 1. In the case of insertion, there's only one single restructuring step. Okay, trinode, but multiple. So this is something very important. So now, in theory, how many rotations do you think you might need? Or how many restructuring steps do you think you might need in the deletion, in the worst case? And remember, the way we're going to go up is by going from n, which is the one to be deleted. In the worst case, n could be maybe very close to the bottom of the tree, right? In that case, if you go all the way up to the root, you just found that you're so unlucky. You got to somehow restore the balance for almost every ancestor along the way. In that case, how many, asymptotically, how many trinode restructuring steps do you need to do? Anyone? How do we express that? Let's answer that, and then we'll go back to example, yeah? Big over n? However, why would that be big over n? If we only talk about ancestors' path, we're not really going over the whole tree. Remember what we're doing here? The tree we start with is like a balanced binary search tree. We just temporarily find that the very last deletion has temporarily caused an unbalance. So we just go all the way up. At this point, the height of the tree will still be more or less about big of log n, right? So this is not the way to go, all right? Okay, it should be big O of h, which will be the height of the tree. And since the tree we are talking about is still more or less Strictly speaking, it's not exactly balanced, but still more or less asymptotically balanced, which we go of log n. Okay, this one tells you if you want to restore the balance for the deletion, you will take up to log n in the worst case steps or rotations. All right. All right, I want to highlight some stuff over here to you very quickly, and then we'll go ahead and do one example. Okay. So once you find out the very first node that's unbalanced, let's say that's called an A. Okay. Again, we got ABC. That's why it's called tri-node restructuring step. A here is the lowest node. Okay. So this is the lowest unbalanced node. A here. Now, in the case of insertion, we said we simply choose B to be the child along the ancestor path, right? But now in this case, a little bit different. Let's say A here has two children. Let's say has let's say child number 1, or let's say left and right. That might be a little bit easier. This might be a left child of A. It might be a right child of A. Now, which one do we choose? Okay, according to the algorithm, you choose the taller child. So let's say this is the height of A, and this is, so let's say this is height number 1. Let's say this is height number 1, and this is height number 2. Choose a larger one. Okay, so let's say, assuming that H2 is larger than H1. In that case, you got to choose this one to be B. Taller child. That's about how you choose B. All right? And then we talk about how do we choose the C? Let's say B is here. So we already got A and B. So we got A here. Okay, let me just do it better. So we got A here, and also we got B here. So now how do we choose C, finally? It really kind of depends on the slant, okay? You want to look at the nodes again. There are two cases. So here, let me try to maybe write. Okay, let me just try to draw that over here. Okay, that'll be better. Let's say we have already got this. We got A, and then also we got B. And then we got to choose the C, right? Let's say B has two children. Okay, case 1. And also case 2. Also we got A here, and then we got B here, and then we got two children, okay? Why don't we say this is the left of B. This is the right of B. And this one here, again, is the left of B, and this is the right of B, okay? So case number 1, if their heights are different, again, choose the taller one, okay? So let's say we got H1 and we got H2. If H1 is not equal to H2, choose the taller child. Okay, depending on which one. For example, let's say maybe it's that, for example, H2 is larger than H1, let's say. In that way, you will choose this one here as C. Choose a taller one if the heights are different. Case number 2, what if the heights are the same? H1 and H2. In that case, we look at how A to B is slanted. They're slanting to the right in this case. In that way, choose the one that's going to keep the same slant. Because if you remember, if we got this particular slanting orientation from insertion, we only do a single rotation on the middle node B. On the other hand, if we choose this one here to be C, A, B, and C, in that case, we have to do a double rotation, which will give us a little bit more work, right? So that's why, okay? Just an algorithm. Okay. So if H1 equals H2, choose the child that will make A, B, C slant the same way. Okay, in that case, we're gonna have the C right here, okay? So it really depends, okay? But we'll see that in the example, okay? All right, so that's about the principle here. Let's now just do one example, okay? Together, okay? And the example I think we can do is this. Okay, let me just show you the slides and then let's now do that one, okay? Okay, let's now do this one here, the simpler one, just for today. All right, guys, how about this? You know the step. Build this binary search tree, okay? And annotate the heights as well. I can tell you that this exercise here will only involve a single restructuring step, only one. Okay, it's not going to be log n. Log n, I'll leave that as exercise for you. You can spend a little bit more time trying it. Okay? Just don't forget to also draw the external nodes. Okay, take 1 more minute and then make sure you also annotate the heights to decide whether this initial binary search tree is actually balanced. Okay, I'm done on my end, but I'll wait for you. Okay, take a little bit of time. Yeah. Okay, let's compare this. All right, it should be something like this, right? So you got 44. Okay, if you do in order traversal, 30. Oh, what am I doing? Oh, I'm sorry, so embarrassing. I got it wrong. Okay. Let me fix it. Okay. Don't be like me. That's my advice. Give me 1 minute. I'm going to fix it. Okay. Give me 1 minute. Yeah, almost done. Keep missing something. Okay. Sorry for causing the delay. Almost there. Okay, good. That should be the one, right? Okay, right. So 17, 17, 32, 44, 48, 50, 54, 62, and then 78, 88. Okay. And then heights. 0, 0, 1, 0, 1, 2. 0, 0, 1, 0, 0, 1, 1, 1, 2. 0, 0, 1, 0, 1, 2. 2, 2, 3. 2, 3, 4. All right, so balanced. All good. So this one here is balanced. All right. And now take 30 seconds or 1 minute. Can you delete 32 and show the result in another tree? All right, this one shouldn't be too difficult. All right, you can see 32 is right here. This is basically case number 2, where the node to delete has 2 external child. Simple case. Okay, but when you get to the exercise I'm going to assign to you, it will be slightly more complicated, but still doable. All right. So we're going to delete this node here, and the way to do it is we're going to delete it and convert that node into external, right? So what we'll do is we're simply going to delete it. Okay. The way I'm going to delete is just wipe it out. Okay, like that. And this one here is just going to be an external node. Right, it's been deleted. And we're now going to update the heights. 0, 0. So that means this one will be 1. 3, 1, 4. Right? Is this tree balanced? No, apparently not, because right here, the difference is 2. All right, that's good. So you can see that this node here is the lowest one. That's unbalanced. You can think about we are basically following this particular ancestor path, right? Because the node was deleted, so it's basically the node that's left. So you basically go this way, right? And then we find that this is the node. That's the lowest node that's unbalanced. I'll just put it like that. Okay. So this will be A. Now, A is chosen. If we were doing insertion, you would have chosen this, the child is the B, right? If that's insertion. But not the case anymore for deletion. What was the rule? Do you remember? Taller child. This child here, height is 1. This child here, height is 3. So this child here should be B. Okay? That's a critical bit. So this one here is B. That is the taller child. How about C? Somehow, for this B here, it has 2 children. They have the same heights. Which one should we choose? Should we choose this one here? Or should we choose this one here? Which one? 50 or 78? 78. That will slant the same way, right? That's a principle, right? A and B already slant this way. So you got to choose this one so that it slant the same way. All right? Good. So this one here is actually going to be C. Equal heights. means choose C such that A, B, C slant the same way. Of course, in the test, you don't need to say that, right? You just know how to choose it, right? I just want to show you the sketch work. All right, so we got A, B, and C. Now, question for you. Should we do a left rotation or right rotation? Left, right? We somehow want to promote the B here up into the root. All right? So we have done this actually quite a few times. Can we just speed up the process, right? So let's think about it this way, okay? So we're going to do a left rotation on B. All right, let's now lay out A, B, and C. So B here is 62. A here is 44. C is 78. Right? If you like, I can just do some quick annotation. C here, and we have A here, and oh, beg your pardon, that's B. Yeah, sorry about that. That one there is B, and 78 is C. Right? All we got to do is figure out T1, T2, T3, etc. Question?
Is there a reason why you couldn't do a right-left rotation on 50?
It's a good question here. Just the algorithm itself simply specify you want to slant the same way so you can avoid doing double rotation. So sometimes maybe in this case, double rotation might somehow will either result in the tree not exactly restore for its balance, which is more work. Yeah. I think that maybe, but in the actual test or maybe the exam, we'll just follow this algorithm here. Yeah. All right, very good. So let's now see this, right? You can see this part over here is T1. Okay, let's just do some very quick annotation. So this part over here is T1, right? And then for B, this will be T2. The left child of B will be T2. And then the left child of C will be T3. And this part over here will be T4. Okay, we're just going to lay them out, T1, T2, T3, T4, nicely. Okay, let's now recreate it. So this will be a little bit closer to how you're going to solve it in the actual test, right? Once you get a little bit more proficient. So this is going to be T1, 17. And also T2, which I got 50, and then 48, 54, and then T3 itself is just external. And T4 is 88. Okay, like that. That's what we have. And let's double check if that's balanced. So 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 2. 0, 0, 1. This is 0, 0, 1, 2. 1, 2, 3. Okay, 2, 3, 4. Balanced. Okay, balance again. Of course, right after the deletion, it was not balanced. And then, of course, this one here is not balanced. All right. So the exercise for you to try, I think we should really end pretty soon today. We only got 4 minutes. So this will be something for you. But this one, the way I laid it out, you're going to need more than one tri-node restructuring step. So I would say this will be a nice exercise for you to really review the algorithm about its deletion and also to see how you can do tri-node restructuring steps. Right? That's something I'll leave to you. And also give you the solution. Okay? So next Friday, we'll still be in person meeting here. The lecture, I'm going to start covering graph starting from Monday. So I think the Java exercise I assigned to you about tree rotation, we also go over that on Friday as well. And there'll be some new exercises we're going to do in the next Friday. All right, thank you so much. Have a good weekend. I'll see you next Monday.